Welcome to this explainer, 90 minutes to glory. That is exactly what you have when you step into the exam hall for your Cambridge physics paper. Today, we're decoding an absolutely crucial part of the Cambridge syllabus. Whether you're taking code 0625, 0651, 0652, 5054, or 9702, we are mastering the concepts of background radiation and, more importantly, the exact strategic frameworks you need to absolutely ace your exam. Picture the extreme tension in the exam room right now. You've got the clock ticking down, it's high pressure. Let's look at two candidates facing the exact same real past paper question. We have Alex on one side and Sam on the other. Now, Alex has literally memorized the entire textbook. Alex overloads the answer with raw physics facts, dumping every single piece of knowledge onto the page, but completely forgets to provide any actual analysis. It's just a massive, unreadable wall of text. Then we have Sam. Sam knows the physics, but the pressure is intense. Sam rushes, completely misses the specific command word requirements of the question, and basically answers a question the examiner didn't actually ask. If you look at their flawed answers, you'll see the red pen of doom everywhere. They both left incredibly easy marks completely on the table. The goal today is to transform you from an Alex or a Sam into a top-tier candidate with a flawless, bulletproof game plan for exam victory.
Here is exactly how we are going to break this down today. 1. The background radiation challenge. 2. Core radiation principles. 3. The technical methodology. 4. Critical analysis strategies. And 5. Examiner insights and warnings. Let's jump right in. Section 1. The background radiation challenge. We are starting with a stark warning directly from the source. The post-match analysis of the examination board itself. Principal examiner reports explicitly reveal that candidates consistently confuse key terminology. The examiners pinpoint this confusion as the absolute primary hurdle for students. What does this look like in reality? Well, it looks exactly like Alex from our earlier example, writing down a phrase like the radiation level instead of specifically writing count rate. It looks like candidates using the word activity loosely when they should actually be talking about the corrected count rate. Look, in physics, words have highly specific mathematical definitions. When you confuse them, the examiner literally cannot award you the marks, even if they suspect you secretly know the right concept in your head. Precision is your absolute best friend here. If you write vaguely about background stuff, the red pen is coming out. You must use established, rigorous terminology. Before we continue, subscribe to our YouTube channel, Ace the Exams, at Exams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. This brings us to a really fundamental question. Why do students find applying concepts to unfamiliar contexts so incredibly hard? While you might memorize facts from a textbook perfectly, the real difficulty lies in transferring that knowledge to the unique, unfamiliar scenarios presented in past paper questions. Cambridge is famous for this exact trick. You might learn about background radiation in a standard, boring laboratory setting, right? But then the exam question will turn around and ask you to analyze the radiation readings taken by a probe near an active volcano, or aboard an International Space Station, or inside a high-tech medical physics facility. If you have only memorized the isolated facts without understanding the underlying principles, your brain just freezes when the context changes. The solution? We don't just memorize. We build a strategic framework that can be applied to literally any bizarre scenario they throw at you.
Section 2. Core radiation principles. Before we can build complex analytical arguments, we need to completely secure our theoretical building blocks. There are 4 primary sources of background radiation you must be able to cite instantly when asked. First up, we have radon gas. This is a heavy, radioactive gas that naturally seeps up from the ground, specifically from the radioactive decay of trace amounts of uranium found in rocks and soil. In many parts of the world, it is actually the largest single contributor to background radiation. Next, we have rocks and buildings. Materials like granite naturally contain radioactive isotopes, so that fancy kitchen countertop, yep, slightly radioactive. Then we have food and drink. Yes, the actual food you consume, like bananas, contains naturally occurring radioactive isotopes such as potassium-40. Finally, we have cosmic rays. This is high-energy radiation pouring in from the sun and deep space that constantly collides with our atmosphere. If an exam question asks you to identify natural sources contributing to a detector's base reading, this is your definitive go-to checklist. Lock these 4 in your memory right now: radon gas, rocks, food, and cosmic rays.
So, now that we know where all this background radiation comes from, how do we actually measure it? You need a precise, examiner-approved definition for detection. Detection involves utilizing a specific detector, which is most commonly a Geiger-Müller tube, and this is connected to a counter. This setup measures the count rate. Now, pay incredibly close attention to the units here. This must be expressed in counts per second or counts per minute. But here is the critical point. This is the exact step where thousands of students drop an entire grade boundary. You must correct for the background radiation itself. Think about it. If you are trying to measure the radioactivity of a specific sample in the lab, your Geiger-Müller tube is also picking up the radon gas in the room, the cosmic rays from space, and the rocks in the walls. Therefore, to find the true, actual count rate of your specific sample, you must first measure the background count rate without the sample present. Then, you mathematically subtract that background count from your total count. If you forget to mention this specific subtraction step in a methodology question, you lose the marks. Period.
Section 3. The technical methodology. Now we transition from what you need to know to exactly how to systematically apply it for maximum method marks. This is where we fix the mistakes that Alex and Sam were making. Follow this exact procedural framework during the exam to ensure systematic processing. Step 1. Deconstruct the question. Underline the command words. Are they asking you to describe, explain, or calculate? Each word demands a totally different type of answer. This is where Sam messed up by rushing. Step 2. Extract the data. Pull the hard numbers out of the dense text and write them clearly on the side of your page. Step 3. Select your analytical framework. This is a game changer. We use the PEAL method for extended written answers. PEAL stands for point, evidence, explanation, link. You state your main point, you provide the data as evidence, you offer the physics explanation, and you link it back to the core question. Step 4. Execute with clear notation. Show every single step of your working out. Do not skip steps. And step 5. Present properly. This means using the correct units, like counts per minute, and double-checking your significant figures. If you apply these 5 steps with energy and absolute focus, you transform an overwhelming paragraph into a simple, highly solvable puzzle.
Crucially, cross-topic connections achieve significantly higher marks. Your analysis shouldn't exist in a vacuum. Examiners explicitly reward candidates who integrate knowledge from other syllabus areas. This is how you show you truly understand physics. For example, if you are discussing a Geiger-Müller tube, can you link the concept of ionizing radiation back to atomic structure? Can you explicitly mention how ionizing radiation knocks electrons out of atoms to create a measurable current? If you were talking about background radiation from rocks, can you link it to the concept of half-life and radioactive decay? When you show the examiner that you understand how the entire physics syllabus connects together like one giant puzzle, you instantly elevate your answer from average to absolutely outstanding. Stop scrolling, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Section 4. Critical Analysis Strategies. Let's run a quick interactive workshop to stress test your ability to scan data and write high-speed answers under pressure. We call this the Find the Flaw Challenge. Look at the immense difference between simply stating facts versus identifying similarities and differences using comparative connectives and hard evidence. Imagine you are reviewing a sample paragraph that simply says, Experiment A had a high count rate, Experiment B had a low count rate. That is exactly what Alex would write. It is just stating raw facts and it scores 0 for analysis. You must identify similarities and differences using connectives. A top-tier candidate rates something like this. Whereas Experiment A recorded an uncorrected count rate of 500 counts per minute, Experiment B demonstrated a significantly lower rate of 150 counts per minute. However, both experiments failed to subtract the background radiation baseline of 30 counts per minute, rendering both final activity calculations inaccurate. Do you see the massive difference there? The second answer perfectly uses the PEAL framework, incorporates data as evidence, uses comparative connectives like whereas and however, and crucially links back to the core concept of background correction. For complex data tables, rely on the deconstruct, solve, evaluate method outlined here to draw out your evidence-based conclusions. First, identify the given information in the chart. Second, break the problem into logical steps. If they give you a total count rate over 10 minutes, your first logical step is to mathematically divide by 10 to get the counts per minute. Step 3 is to solve systematically, which usually means subtracting the background radiation. Step 4 is absolutely critical. Check for reasonableness. If your calculated background radiation is 5,000 counts per minute in a normal classroom setting, you have definitely made a math error. Background radiation should typically be a very low number, generally around 20 to 50 counts per minute depending on the specific environment. Finally, step 5. Make justified recommendations. If an experiment's count rate is barely hovering above background levels, you should confidently recommend running the experiment for a much longer duration to gather more statistically significant data.
Whenever an exam question asks you to evaluate the quality of evidence or critique an experimental setup, you must systematically check these 4 requirements. 1. Identify limitations. For example, remember that radioactive decay is entirely random and spontaneous. A major limitation of measuring radiation over a very short period, like just 10 seconds, is that random statistical fluctuations will heavily distort your final results. 2. Note assumptions made. Are we blindly assuming background radiation remained perfectly constant during the entire experiment? 3. Consider alternative interpretations. Could a sudden, massive spike in the count rate simply be due to an external factor, like a medical radioactive source being moved in the room next door, rather than the sample itself? And 4. Assess the effect on conclusions. If the background radiation was not subtracted, your final conclusion about the sample's activity is fundamentally flawed because the numbers are artificially inflated. Nailing these 4 points in rapid succession will secure you maximum marks in the absolute toughest evaluation sections of the paper.
Section 5. Examiner Insights and Warnings.
We have scoured the principal examiner reports to bring you the exact pitfalls that cost students their top grades. Let's look at how the grader actually thinks. There are 3 specific mistakes frequently and harshly penalized by examiners. Mistake number 1. Answers are simply too vague. Writing something like radiation comes from the environment is way too vague. You must specify radon gas in the air or cosmic rays from space. Mistake number 2. Forgetting to check format and presentation conventions. This means dropping proper headings in your data tables, forgetting to write units like counts per second, or failing to show clear annotation of your math steps. If you just miraculously write down a final number without showing the background subtraction process, you completely lose the method marks. Mistake number 3. Answers are not specific to the given context. This is huge. If the question asked about the background radiation risks for a commercial pilot flying at high altitudes, and you write an amazing paragraph about radon gas in residential basements, you will score 0. You must intensely tailor your answer to the specific context, which in this case means focusing heavily on increased exposure to cosmic rays at high altitudes. To permanently combat these vague answers that frustrate examiners, internalize this one golden rule. Always define terms before using them in extended responses. If you are writing a 6-mark answer about an experiment using a Geiger-Müller tube, make it an absolute, non-negotiable habit to explicitly define your terms right at the start. Write a clear sentence stating, background radiation is the ambient ionizing radiation present in the environment from natural sources such as cosmic rays and radon gas, which must be subtracted from the total count rate to find the sample's true activity. By putting that crisp definition right at the top of your paragraph, you instantly signal to the examiner that you are a precise, highly rigorous candidate. It sets the perfect tone for your entire answer and practically guarantees you pick up those initial knowledge marks before you even begin to tackle the complex calculations.
So, the choice is entirely yours. Will your next exam answer be a scattered, panicky list of vague facts like Alex, or will it be a systematically processed, context-specific strategy using Peel? Mastering physics isn't just about memorizing radiation sources. It is about executing a highly disciplined strategy under extreme time pressure. We have given you the complete answering system today. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, ACEDEAMS, at ACEDEAMS_IGCSE to excel in your Cambridge examinations. Subscribe right now to @ACEDEAMS_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.